So we are starting with May-June 2021 paper 42. This paper is of 30 marks, but like I said, from 2023 onward, all the papers of ADP would be of 40 marks in the same time, 1 hour. Let's start off with the first one. A student investigates how the potential difference. Uh, we have had so many questions about potential difference across a fixed resistor are changes as extra resistance is added to the circuit, and then there is a circuit that they have shown. So all right, so they are adding the extra resistance from here, and the fixed resistance is over here, which is connected with the battery. There's a switch as well, and across the resistor there's a voltmeter over here. All right, she connects the crocodile clip. All right, this is called the crocodile clip, this thing, to a point on the resistance wire at length 20 centimeter from end X. So what they're saying is this length L, small l, equals to 20 centimeter, like from here till the point C. This length is 20 centimeter. He closes the switch, means the circuit is turned on. She reads the voltmeter and records the reading. She opens the switch. Figure 1.2 shows the voltmeter reading. Then there's voltmeter reading as well. Read the voltmeter scale in table. On page 4, record the potential difference. And it should be pretty much simple. 1, and from 1 to 2 we have 10 divisions. So this one would be 1.4. Okay. So in the middle of 1 and 2 we have 1.5. So this little longer line is representing 1.5, and we have one line behind 1.5, so that means 1.4. Calculate 1 over V and record its value in table 1.1 on page 4 to the appropriate number of significant figures. So first of all, this one was 1.4. We can record it over here, 1.4. Then we need to find the value of 1 over V. So this one represents the quantity that we need to find, 1 over V, 1 over of potential difference, and this 1 over V is the unit. Now we can hit it on the calculator. We take out the scientific calculator. We do 1 divided by 1.4, and what we get is 0.714, and recurring something 0.714, but we have to write to appropriate number of significant figures. The entire data is in 2 significant figures, so in 2 significant figures it would be 0.71. So 1.4 against 0.71. She repeats the procedure in A using the values 30, 40, 60, and 80. Her results are shown in the table 1.1. Suggest why the student opens the switch between the readings. So when they say she opens the switch between the reading, So basically she's disconnecting the circuit after every reading. So there's a very generic answer for any question that is related to the circuits, and they say, why do you need to keep the switch off time to time or after every reading? Or why do you need to keep the switch open? When it's open, it means it's turned off. And the answer is, a generic answer is, to avoid the cell run down too quick. Right? So there are some other acceptable answers as well. For instance, we can say to avoid the resistor getting too hot, because if the resistor is hot, its resistance would be changed. This is a concept that we study in electricity. But if we want to keep it simple, more practical, we can simply say to avoid the cell running down too quick. All right, on to the next one. On the grid provided in space 1.3 on page number 5, plot a graph of 1 over V on y-axis and L on x-axis. And that is once again 4-mark question. So I should label it once again. We have to cover up 4 marks in such a way. Now the first mark is for labeling the axis. Second mark is for choosing a proper scale. Third mark is for plotting the data. And fourth and final mark is for drawing the line or the curve, depending on the question. So let's consider the first one first. We have to label the axis. So y has to be represented, representing 1 over v. So let's do that. This one is the y-axis. So on y-axis we are representing 1 over v, and the unit of 1 over v is also 1 over v. In the unit v represents volt, and in the quantity over here we represents potential difference or voltage. Then we have to label length on x-axis, and length is being measured in centimeters. How do we know that? We know it from the table. So we write length in centimeters. Length would be measured in centimeters. And like I said, the next step and the most important step. So labeling is done. When I say the word label, it means you have to label with the proper units. Only then you get a first mark from here. The scaling is the most important step. You have to scale the axis so that it follows certain criterias. One of the criteria is at least 75% of the axis should be covered. So we had to label x-axis. We had to represent length on x-axis and this thing on y-axis. Now let's think about a scale. First of all, we have to see if they have limited us with the scale. And yes, there is a limitation. It reads start both axes from origin, from 0 0. So in that case, we cannot start the axis or the length. Let's say we cannot start from 20 or 10, because all the values of length start from 20. So it would be very convenient to start the x-axis from 20 or 15 or 10, because we don't even use any value under 20 centimeters. But since there's a limitation, so we have to start from 0, and our values go all the way till 80. All right, so let's label the axis. So what I can do is, after 10 small blocks, I'm going to representing 10 centimeters on the x-axis. So this one would be 10, and after next 10 blocks would be 20, next 10 blocks 30, next 10 blocks 40, next 10 blocks 50, next 10 blocks 60, next 10 blocks 70, and the next 10 80. And you see, you have scaled the axis in a way that 80%, around more than 75% of your axis is being covered, which is the criteria. And in this case, I mean, we are on the very safe side. Almost 90% of the axis is covered. The x-axis is done. Now let's think about the y-axis. On the y-axis, the values start from 0. Obviously, they have stated all the values should start from 0. And the maximum value that we are having is 1.3. All right. Generally, this is general rule that scaling for the y-axis is slightly dramatic in the table. So you have to be very careful with it. Try to keep it an even number. Even if it's in decimal, forget about the decimal. Just try to keep the last digit an even number. So what I can do for this one is, since I need to reach till 1.3, I'll be just assuming that I need to reach till 1.4. So what I can do is, after every 10 small blocks, I'll be representing 0.2 per volt. So after next 10, I'll be having 0.4. After next 10, I'll be having 0.6. After next 10, I'll be having 0.8. Then 1.0. Then 1.2 here. 1.4 here. And you see, using such a scale, we have used pretty much in the entire axis, more than 90%. So we are on the safe side. That scale is acceptable. Or you could have also used, after 10 blocks, we can have 0.25. In that way, your y-axis would have been compressed a bit, but that too and this one, both are acceptable. So once you're done with the scaling, and if it is done properly, if the scaling is not too dramatic, then you get 1 mark from here as well. The third one is kind of an easy mark, because you simply need to plot the data. The first point that we have is 20 on the x-axis, 0.71 on the y-axis. So let's take a look at that. 20 gives 0.71. So we get 20 from this line, from the x-axis, and for 0.71, let's take a close look of the y-axis. So we'll be having 0.7 in the middle of 0.6 and 0.8. In the middle of 0.6 and 0.8 we'll be having 0.7. This one would be representing 0.72. This one would be representing 0.74. This one would be representing 0.76. Then 0.78. Only then we'll be having 0.8 at the bigger line. So now I know this one small block represents 0.02. So this one is 0.72 and the mark 0.71 would be exactly in the middle of these two lines, in the middle of 0.7 and 0.72, because you can think about 0.7 as 0.70. So 20 from the x-axis and 0.71 from here. So the mark would be someplace over here. Mark should be sharp, should be minute. It should not be kind of a blob. If you draw like this, Cambridge says it is a large blob and they are tempted to deduct a mark in that case. So the second point, let's speed up from here. The second point was 30 against 0.77. All right, 30 from the x-axis and 0.77 from the y-axis. So 0.77 would be between 0.76 and 0.78. Just a quick look over here. This one would represent 0.76 and the upper one would represent 0.78. In the middle of it, we'll be having 0.76. And it has to be plotted against 30. So it would be someplace over here. So now we're done with the first 2 points. The next one is 40 40 from here and 0.91 from here. 40 against 0.91. So it is very easy to locate 40 from the x-axis, no problem from there. And 0.91. Okay, so first of all, 0.9 would be in the middle of 0.8 and 1. And the next line after 0.9 represents 0.92. So for 0.91, it would be in the middle. Yeah, sorry, for 30, it was here. All right, 40 against 0.91, it would be someplace over here. 30 from here, from the x-axis, and 0.9 from here. All right, the next one that we have is 60 against 1.1. Yeah, 60 against 1.1. So 60 from the x-axis. This one is representing 60. 60 from this side and 0.11. So 0.11, first of all, this is 1.0. Sorry, 1.1. It was how much exactly? Yeah, 1.1. So 1.1 should be very easy. If this one represent 1.0 and the upper one represent 1.2, so 1.1 would be exactly in the middle. So this one would be over here. this one. Then we have the next one, 80 against 80 against 1.3. Let us plot this one as well. 80 from the x-axis. So 80 is, this one line is 80, and it was to be represented against 1.3. So 1.3 is once again very easy to locate. It would be exactly in the middle of 1.2 and 1.4. So it would be exactly over here. Try to keep it a small dot. So this is what we have once we have plotted the data. And if you have plotted the data accurately, you get +1 over here. You get the mark for plotting as well. Now the final thing is we have to draw best fit straight line. The criteria for the best fit straight line is you need to see the pattern. You need to see the pattern of the dots, and you need to draw a line in such a way that majority of the points are covered. If they're not being covered, then there should be equal distribution of points above and below the line. So the line should be very minute, should be very sharp, and a single smooth line, no doubling or no nothing with it. So if I pass the line for like some place from here, now I can just stretch it back. So yeah, this one would be the best fit line because we have pretty much even distribution of the points below and above the line. You see, the point that was below the line, it is compensating for the points that are above the line, because the points that are above the line, that are quite close to the line as compared to the point that is below the line. So that's why the line has to be a little bit closer to the points that are above, because we have to compensate for the two effects. All right. Calculate, the next part reads, calculate the gradient m of your line. Yeah, you get 1 mark. The last mark you get is for drawing the line and the curve. In this way, you complete 4 marks for the question of drawing the graph. Part D, part 1. Calculate the gradient m of the line. Show all working and indicate on the graph the values you use. So, very popular question that is followed right after the graph question, to find the gradient of the line. And what do we do in that is we choose 2 points on the line which are not too close, which are like pretty far from each other, and the point should not be too dramatic. When I say too dramatic, I mean you should not be wasting so much time in finding the value of x and the value of y for that point. Or if you're familiar with mathematics, then I can simply say the coordinates of the point should not be too dramatic. So I can choose this one from here, and the coordinates would be 10 against 0.6. Yeah, that looks like a good one here. 10 against 0.6, and the other one should be quite far from here. 2 points should not be too close, and it has to be on the line. We cannot simply choose the points from the table. All right, so the second one, Yeah, this one looks good. Let us write the coordinates. So 1.2 from the y-axis and 71.5 from the x-axis. Because it's someplace over here. If I stretch it down, extend it downward, it's someplace over here between 71 and 72. 71.5 from the x-axis and 1.2 from the y-axis. 71.5 and 1.2. 71.5 with 1.2, and the second one was, or the first one, 10 against 0.6. Then for any of them, you can call this one x1, this one would be your y1, this one would be your x2, this is your y2. Now for finding the gradient, we can apply the formula that we study in mathematics as well. Y2 minus y1 over x2 minus x1. Then you insert the values, 0.6 minus 1.2 divided by 10 minus 71.5. You write down you insert the fraction button on your calculator, insert all the values on the calculator, and just press the equals to button. So what do we get for this one? And 0.009 followed by any other digit do we have? So 0.0097, yeah. So 0.0097. If you want to write in one significant figure, then that would be 0.01. And whenever you have a question that is to find the gradient of the best fit curve, they always expect the answer within a certain range. There's a not, they don't expect a strict value because there's always some variation when you have to draw the best fit line or the best fit curve. Like for this one, if I write it over here, the accepted range for this one is this. So what they're saying is any value between 0.0095 to 0.015. Any value between that is acceptable. So 0.0097, that too is acceptable. If you want to write till to only one significant figure, which would be 0.01, that too is acceptable. The next part says extend your line until it crosses y-axis. Measure the y-intercept. Intercept C that your line makes with the y-axis. So basically, we need to measure the y-intercept. And in graphs we study in mathematics that y-intercept is a point where the line cuts the y-axis. So let's check it from the graph. Our line was intersecting y-axis at the point in the middle of 0.4 and 0.6. Yeah, exactly. It would be 0.5. So we can safely write our y-intercept is 0.5. I'm just drawing a bubble here because I don't want to draw a dot. Dot represents the point that we plotted from the table. So this one was 0.5. The question followed by that, calculate the electromotive force E of the cell using the equation. For ADP, you don't need to memorize any formulas because whenever they ask you a question about calculating a physical quantity, they provide the formula. So K, they have stated, is representing 1.0 divided by the value of C, which was 0.5. So you divide 1 with 0.5, you get 2. Do we? All right, part F. So here we have this one, part F. It reads, suggest one practical reason why, despite carrying out the experiment with care, the student's value for E may not be the true value. So the thing is, the student had to select the length 20 centimeter first. And how does he do that? He needs to place the crocodile clip exactly at 20 centimeter mark. Then he needs to place the crocodile clip at 30 centimeter mark, then 40 centimeter mark, then 60, then 80. So when he is placing the crocodile clip or is attaching the crocodile clip, there's every chance that there's some variation of some centimeters. He wants to place it like 40, but it is indeed on 41 or 39 because the crocodile clip, the face is not very sharp. It covers a lot of values. So we need to place it exactly in the middle, which is always prone to an error. So he may not be placing the crocodile clip at exact length. That can be one of the reasons. Part G. The results in the table 1.1 shows that as the length L of the resistance wire increases, the potential difference V decreases. So what they're saying is when the L increases, the potential difference decreases. State how the results show that L is not inversely proportional to V. So if something is inversely proportional, there's a rule for it that the product, we study one thing like in the chapter of gases, thermal physics, we studied pressure and volume are inversely proportional to each other. And if they are inversely proportional to each other, we were able to write an equation that looks something like this. P1V1 equals to P2V2. That means the product of pressure and volume for a fixed mass of a gas is constant. So the product of P and V for all the points would be constant. If the pressure is 2, the volume might have been 20. But if the pressure is 1, the volume might have been 40. In both cases, the product would be 40. Product would always be same if they are indeed inversely proportional to each other. But for this case, if you use the same logic in this one graph, you'll find out that if you choose uh, 1 or 2 sample points, 2 or 3 sample points, then the product of V and length from the table would not be constant. What I'm saying is, take the length from here, multiply it by the potential difference against that length. Take the other one, length multiplied by the potential difference against that length. Take the next length multiplied by the potential difference against that length. The answer would not be same. You can hit it on the calculator and check it. And if the product is not constant, then the quantities are not inversely proportional to each other. So we write since L into V means the product of length and volume is not constant. Once again, this question can be answered in different ways, and that is one of them. Since L and V is not constant, so L is not inversely proportional to V. And in the question number 2, it looks from the topic of measurements and motion, which was previously called as kinematics. A student measures the acceleration of a trolley rolling down a ramp. Okay, and then the description would be all about the adjustments. I mean, we can also see that it starts from A, starting line is AB, and then from AB till the line CD, the distance is 120 centimeters. He adjusts the height of the top of the ramp above the bench by moving the clamp until the ramp makes an angle of theta, which is 30-degree with the bench. Okay, he places a trolley on the ramp so that the front wheels of the trolley touch AB. All right, state a name of the device that the student uses to ensure AB and CD are 120 centimeters apart. So a very popular answer is meter rule, and the other one is measuring tape. The rule of thumb is we prefer meter rule for the objects that are till 100 centimeter. For the objects longer than that, we prefer tape measure or measuring tape. So for this one, about different measuring tools and what is their range, what is their least count, I made a separate video for these tools. If you have any you want to refer to that, you can watch the video. The second part is the ramp makes an angle of 30 degrees with the bench. What tool do we use to measure the angle? Yeah, exactly. It is the protractor. The student releases a trolley and at the same time starts a stopwatch. It stops the stopwatch when the trolley has traveled 120 centimeter down the ramp. He replaces the trolley at the top of the ramp with his front wheel touching AB and repeats the procedure twice. So he does it first time and followed by that he repeats the same process 2 times more. And the first time he does it, the trolley completed a distance of 120 centimeter in 0.70 seconds. In the second attempt, it completed additional 120 centimeter in 0.81 seconds. And then in the third attempt, the trolley covered 120 centimeter in 0.95 seconds. So just one reason why there is a large variation in the data. So basically what they're saying is what can be the possible reasons for the error. Yeah, that is, I mean, one of the standard answer that you can write with the questions with the experiments related to time. For all the timing questions, timing experiments, one standard answer, one generic answer for the large variation or for the error is due to the reaction time. So the distance is too small for him to react quick enough. So we can write reaction time error. This is a terror, uh, not terror. This is the error that is mostly associated with the timing experiments. And the other answers are also there. I mean, he has to ensure that every time he starts from the mark AB, the tire, let's say the variation can be due to the fact that in the second time the tires are slightly above the line, in the third one the tires might be slightly even more ahead of the line, or um, uh, but if we refer to the data, I mean it's taking more time, so the tire might be behind the line a bit. That's why the trolley is taking more time. But the standard answer and the generic one is the reaction time error. You can always write this one and get away with that. All right, then we need to, this is a side view, but the question is calculate the average time for the trolley to travel a distance of 120 centimeters. All right, so it was 0.70 plus 0.81 plus 0.95. 0.70 plus 0.81 plus 0.95 divided by 3, and the answer we have to write to two significant figures, and what do we get from here is, so okay, so we get 0.82 seconds over here. Yes. Yeah, question number 2 was there. Yeah, part 2 was there. On figure 2.2, draw the position of the trolley when it has traveled 120 centimeters. So yeah, this one is another one where the students would commit a mistake. Uh, when the trolley was at the position AB, at the starting position is in such a way that the front wheel of the trolley are at the point AB or on the line AB. So as soon as the front wheel of the trolley crosses the line CD, we'll say that it has covered the distance of 120 centimeters. So students are very prone to get this one wrong. Um, a very uh, possible error is the students would place the trolley someplace over here. They would say, okay, the trolley crosses 120 centimeter mark when entire of the trolley passes the line CD. But no, since the starting point was measured with respect to the front tires, then the finish point should also be measured with respect to the front tires. Calculate the acceleration of the trolley down the ramp using the equation. Like I said, no need to memorize any equations for ADP. It would be given over there. Give the unit to your answer as well. Okay, so acceleration equals to 2 times of distance. Distance I'm going to use in centimeters. It would be 120 centimeters divided by square of the average time. So 0.82 and then the square of it. And then the next step is to hit it on the calculator as it is. And let's see what we get there. All right, so we're getting 356.9. I'll be writing to 3 significant figures, or yeah, 2 significant figures. The maximum of number of significant figures are 2, so 360. That would be okay. If you write it as it is, no marks would be deducted because they haven't asked you to specify the significant figures. So you can write as it is as well. And especially when you have 0 at the end, then it's not easy to know if that 0 is significant or not, because it depends on the instrument itself. And the unit of acceleration that we studied is meters per second square. We can also, derive the unit from here, because in the numerator we were having distance, and well, we measured the distance in centimeters. We measured it in centimeters, and the average time was measured in seconds. So the square of second would be second square. So you can write it as cm slash second square or cm s minus 2. That is the same thing. The last part of it suggests how the student could modify his experiment so that more accurate value for the acceleration A of the trolley is obtained. So the length of the track was 120 centimeter, and that's too small for him to start and stop the stopwatch. If the length were a little bit longer, 300 centimeters or something, 3 meters at least, then the chances of error would have been decreased and the result would have been more accurate. So one of the ways we can write increasing the length of the track. Increasing the length of the track. And other than that, you can also write some alternate statements. For example, he should be assigning another person to start and stop the stopwatch, and he'll be just releasing the trolley. The other person would be controlling the stopwatch. Also, we can write he can place the sensors, although it is like um, not very much practical to arrange the sensor for the student, but still that is an option that he can use the sensor which would automatically measure the time as the trolley crosses, as the trolley starts from the line AB and reaches the line CD. So these are the alternate statements, but we have to write a single one here. So that's the end of half of the paper, and we'll be seeing each other in the next lesson. Take good care. Allah Hafiz.